Hi, my name is Alex Lopez. This is my lab report for Physics 2212 Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet and tube interaction computationally, compare computational predictions with observed data, and preview the results. The average time to fall was measured to be about 1.10 seconds. And the predicted time with the computational model was 1.129 seconds. The main physics principles used in this lab are the Biot-Savart law, which describes the magnetic field generated by a constant electric current and is given by the equation below, and then the magnetic field of a dipole given by the second equation. And then the picture on the bottom right shows the visualization of the magnetic field lines of a dipole. So for the actual experiment, we used a magnet to model a magnetic dipole and aluminum foil to model a tube through which the magnet fell. So the system here was just the magnet and the aluminum foil, and the surroundings is everything else. And the procedure was that the magnet was dropped through the tube 5 times, and each attempt just measuring the amount of time that it took for the magnet to fall through. Here's a brief overview of the results from the experiment. The length of the tube was measured to be 40 centimeters. The width of the aluminum foil was 5 centimeters. The inner radius of the tube was 15, and then the total radius was 20 centimeters. And the average time to fall, as mentioned earlier, was measured to be 1.1 seconds. This is the first part of the glow script code. So here we just have some initial conditions with mu 0 over 4 pi and the mu of the magnet, which I calculated to be 24.58. And then below that we have the function implementing the formula for the magnetic field of a dipole. And then on the right we just have the scale that was used to view the arrows on the screen and the distance that we were observing them from, followed by initializing the vectors for each of the different arrows. So here we can see on the left, for each of the vectors that we initialized earlier, we are calculating the magnetic field for each of them using the dipole B function that we created earlier, and then initializing an arrow to visualize each of them on the screen. And then on the right, you can see we have all the steps to actually calculate the B at 45 degrees, and then we print that onto the screen. Alright, so some possible sources of error here were possible inaccurate timing of the magnet falling, or the aluminum foil being the wrong thickness. And to answer the what if questions, if the resistivity of the conductor were reduced as close as possible to 0, that would cause there to be 0 resistance, which would increase the induced current, which would make the force on the magnet a lot greater, meaning it would fall a lot slower. And then if holes or slots were cut into the tube, how would this affect the ring currents in your model? If there were holes, that would disrupt the flow of the magnetic current, meaning there would be less force and the magnet would fall faster.